So in the last video I must have gotten cut off by something with the iPad, so we're missing about 3 minutes of video. So this is just an extension onto 5.6. As we talked about with kinetic molecular theory, one of the most important postulates is the idea that kinetic energy is directly proportional to the temperature of a substance. So it might be important at some point in time to find the kinetic energy of a sample of gases, or the average kinetic energy. And we may want to go ahead and ask the question, well, how do we go about doing that? Remember what kinetic energy is. Kinetic energy, maybe from a past physical science or physics course, is related to 1/2 times the mass times the volume squared of an object. So the more mass an object has, the more kinetic energy, or the more velocity it has, the more kinetic energy. Okay, so if we want to change the temperature of a sample of gases, we can change the gas out to a more massive gas, moving at the same speed as the other, or we can speed up the gas particles. So what we'd like to focus on with the end of chapter 5.6 is the opportunity of speeding up the molecules. And how can we calculate the speed of those molecules? Well, that's simply called the root mean square velocity of the particular sample of gases. So if you want to look at the derivation of what I'm going to go through, you can check that out in the book in 5.6. I'm just showing you the overall equation to find the velocity of the particular sample of gas molecules. So this right here is essentially just velocity. Okay, the speed and direction the particular object is going. I know that's a little goofy looking, but that's all it is. And the velocity of these objects, of these samples of gas, depends on two things. As we know, it depends on the temperature, and it actually depends on the molecular weight of the objects, so the molecular, how big that sample of gas is. The other constant that's in there is R, and the one thing we got to keep in mind is that R is going to be a bit different than we're typically used to. R has got to be actually measured in joules per Kelvin moles. The reason is, if we're looking for a velocity, again, we're looking for a velocity, think about what the units are for velocity. Typically, your velocity units equals meters per second. Well, if we used our traditional units for R, which are what? They're liter atmosphere per mole Kelvin. You use the traditional units for M, which are grams per mole. Right, and the traditional units for T, which are Kelvin. You've got no meters and no seconds anywhere. So there's no way for you to get meters per second, which is going to be your velocity, the unit you need. So we can use joules. And joules, again, is a measure of energy, obviously. So we convert R into having joules in the unit. And down here I show you that joules simply equals kilogram times meter squared per second squared. And we'll see how those units cancel out. Joules meters per second at the end of the day. All right. Remember, temperature's got to be in Kelvin, and the mass of a mole of gas has to be in kilograms. Okay, that's an important point. So usually we're used to saying the molar mass of an object is grams per mole. Oops, sorry about that, guys. Grams per mole. This time it's kilograms per mole. Okay, kilograms per mole. It's a little bit weird, but that kilogram that you see right here is going to be used to cancel out that kilogram right there. Alright, so let's do, so your final units are meters per second. So we're going to do an example problem here. We want to find, let me bring up a page, we want to find the velocity of a sample of helium gas at 25 degrees Celsius. Okay, the velocity of a sample of helium gas at 25 degrees Celsius. So we know that T equals 25 degrees Celsius, which is 298 K. And we know the molar mass of helium is 4 grams per mole. Remember, we need kilograms per mole. So capital M, okay, is 4 times 10 to the negative third kg per mole. All right, now if we plug everything in correctly, our root mean square velocity, which I'll just write like this, is going to equal the square root, okay, I want a big square root, of 3 times R, which is now 8 8.3145 joules per mole Kelvin times temperature, 298 K, divided by the mass, 4 times 10 to the negative third, the molar mass, kilogram per mole. All right, let's see how the obvious units cancel out. The obvious units are moles and Kelvin that cancel out. Kelvin, Kelvin gone, mole, mole gone. And you're left with joules per kilogram. Okay, now the final answer here, I'm going to write that up, is like 1,380. Okay, so we're going to get 1,380. Okay, we've got joules per kilogram. All right, that's not yet the final answer. I shouldn't say that that's the final answer, but let's say that that's the final unit, is joules per kilogram. But remember, to square that. Okay, and if we expand that out, remember joules is a kilogram times a meter squared per second squared over a kilogram now. Kilograms go away, where we're left with meter squared per second squared, and the square root takes care of these guys. So at the end of the day, we have meters per second. So the units do cancel out. Okay, and if you do the math, like I said, I think you come up like 1380 meters per second or 1360 meters per second. All right, that's it.